Hey, in this example yesterday, what we looked at was how to break up this force of gravity here, or the weight of this box on this inclined plane. We learned how to break this up into its component forces, and we learned that it has a parallel force parallel to this surface, and it feels a force that is perpendicular to this surface, and we learned how to determine the magnitude of those forces. Well, let's take it a step further, and let's say that the question not only asks us what are the components of this weight here, so what are the magnitudes of each of these forces, but also let's say that we want to figure out what is the normal force, what's the normal force that the box feels, and what's the acceleration of the box if the plane is frictionless. So let's take a look at the first part of this question. What's the normal force? Well, remember that the normal force, we learned that the normal force, that is the force that is perpendicular. So force that is perpendicular to whatever surface it's sitting on. So force that is perpendicular to the surface it's on. And so in order to figure out the normal force, it's actually pretty simple, because we already figured out in the previous video, we figured out the perpendicular force going this way, right? The normal force would be the perpendicular to this surface going the opposite way. So normal force would essentially be this force right here. It would not be opposite of the weight. So some people think that they want to put the normal force like this going up, but remember, the normal force has to be perpendicular to whatever it's resting on. So it's resting on this surface, and so it's going to be perpendicular going this way, like that. And then we could break up that into components and things like that, but we're not going to get into that. We're just going to figure out what is the amount of the normal force on this block pushing this way. Well, we've already determined, in fact, let's think about it like this. For the normal force here, and this force that's perpendicular here, since this box is not accelerating up or down, or at least in this specific direction this way, we can do this. We can say that the normal force plus the force that is perpendicular has to be equal to 0. In other words, those two forces have to cancel each other out because the box is not accelerating this way or this way. Since it's not accelerating this way or this way, we know that these two forces have to be equal, or they have to cancel each other out. And so we've already figured out what the perpendicular force is. We've got it down here. We said that it is the weight of the box times the cosine of 30 degrees. The weight of the box times cosine of 30 degrees. So I'm just going to over here say the normal force. And actually, so really this is plus a negative, right? Because they're in opposite directions. So we would say that like this perpendicular force really should be a negative force, and this up here would be a positive force if we assume that this way is positive and this way is negative. And so really what we want to say is that the normal force minus the weight times the cosine of the angle is going to be equal to 0. So again, hopefully that right there makes sense, what we're doing there, right? So we're putting that minus in there because, again, of the opposite directions and the fact that those two things have to cancel each other out because the box is not accelerating in either direction. And so what we've got is the normal force minus my perpendicular force, which is equal to the weight times the cosine of the angle. And that's all of that has to be equal to 0 because the net force in that specific direction needs to work out to be 0. So I can rearrange that again. The normal force, just add this to the other side, right, is going to be equal to the weight times the cosine of the angle. Basically, that's the long way of saying that our normal force is going to be equal to whatever this perpendicular component is, just in the opposite direction, right? And so the magnitude of that force is going to be the same as the magnitude of this one, 43.3 newtons. So our normal force is also 43.3 newtons. Now let's take a look at the second part of that question. Second part of that question says, what's the acceleration then of the block if the plane is frictionless? Well, first of all, we need to bring in Newton's second law here, because this is what we need in order to figure out acceleration in this case. We learned in the last unit that using Newton's second law, acceleration is equal to the force divided by the mass. Force divided by the mass. And we should say the net force, right? The net force. Well, if I come back here and we look at this and we assume that this box is sliding in this direction here. Okay, so it's sliding down this hill like this. If that's the case, and there is no force working back against it, so there's no force of friction. If there was a force of friction, then I would have to figure out what's my net force. But in this case, there is no friction. And since there's no friction here, that means my net force in this direction is just this. It's the parallel force, because that's the only force that's acting on it parallel to the plane. And so we can come back over here, and we figured out, by the way, down here that the parallel force is equal to the weight times the sine of the angle. Weight times the sine of 30 degrees. So I'm just going to replace my net force here. In this case, the net force is the weight of the box times the sine of 30 degrees. All over the mass of the box. But here's the thing, we can take this a step further again, and notice I've got weight over mass, weight divided by mass. If I come back over here, you'll see that weight divided by mass, let's look at this, let's get rid of this for a second, because remember, force of gravity and weight, they're interchangeable, they mean the same thing. The weight is equal to mass times the acceleration of gravity. So if I take this, divide by mass on each side, you'll notice that I get weight over the mass. Weight over the mass is equal to the acceleration due to gravity. So in other words, over here, what I can do, here I've got weight divided by mass. I can just replace that with the acceleration due to gravity. And so really what this becomes is the acceleration due to gravity times the sine of the angle, 30 degrees. And so really, acceleration is equal to this, just the acceleration due to gravity times the sine of that angle. So acceleration is equal to g sine of 30 degrees. If, now again, because in this case it's frictionless, right? It is frictionless, so we don't have to worry about that. We just plug in for our net force there, whatever that parallel force is. But it ends up simplifying into this, and so we can solve this just by doing 9.8 meters per second squared times the sine of 30 degrees. And if we were to punch those in, we would get an acceleration of, what does that work out to be? 4.90? 4.90 meters per second squared.